if applicable. Well, let's do an example here where I have a cantilever beam with a point load at the tip of 40 kips. This is already the ultimate design load. The beam has a depth of 32 inches and a D of 29 inches and a base of 20 inches as shown here. From simple statics, you get that the moment at the critical section here is 240 kip feet, right? That moment is like that, and a shear force of 40 kips, which is the same as the load. In this case, the critical section is at a distance D away from the support, but it's still 40 kips. In this case, we are, just for simplicity, I'm neglecting the self-weight of the beam, which will be probably very small compared with the 40 kips. Okay, so let's design for longitudinal reinforcement. Let's say we pick 2 number 9s. That gives us an area of steel of 2 inches square. We can then compute the depth of the compression block by the familiar expression here, and we get 1.76 inches, which, if we put that into our equation for nominal moment capacity, we get 281 kip feet. Multiply by phi equals to 0.9, and we get 253 kip feet, which is larger than the 240, which means that our design is satisfactory for bending. So we can use 2 number 9s. Then we can proceed to check shear capacity. We'll use the simplified expression 2 square root F prime C PD multiplied by phi. And if you run through those numbers, you get that the shear capacity is approximately 55 kips, which is larger than the ultimate design shear of 40 kips, which means that our design is satisfactory for shear. Now, we need to provide enough development length for this bar right here to be anchored into the wall where the cantilever is coming out, and we need to check that the length of the cantilever is enough to develop the bar in the other direction, right? So we need to develop the bar this direction, and we need to develop the bar in that direction as well. If we go back to our table, and we certainly fall into the category of case 1, since we are providing transverse reinforcement and we are also providing enough spacing between the rebar. So we are definitely in case 1, and we are using number 7 or larger. We're using number 9, so we are going to use this expression right here with Fy as 60,000 psi, F prime C 4,000 psi, bar diameter 9/8, and a lambda of 1 since we're using normal weight concrete. The factor phi sub t for bar location is going to be 1.3 because there is more than 12 inches of concrete cast in the member below the development length splice. And this bar is uncoated, so we use a phi sub e of 1.0. If we put this into the development length expression, we obtain a development length of 70 inches, which is 5.78 feet, which means that we need to provide 70 inches of straight bar development inside the wall and 70 inches on the cantilever side. Thankfully, the cantilever is 72 inches in length, so that works out just fine. And so this would be an example of anchoring a straight bar for a beam subject to moment and shear like shown here. Now suppose you don't have 70 inches inside of the wall, so you could use a hook. In this case we can use the development length for a hook as shown here. If we put in the various values for the various coefficients, we get a development length of 21.3 inches. We need to round up to 22, and so we get 22 inches of straight development plus a hook 12 times the diameter of the bar, which gives us approximately 14 inches, and this will be the setup for a hooked developed bar in this design problem. We still have to provide the 70 inches this way, but we're able to reduce it by using the hook into the wall.